Good evening. Welcome to the second video lecture. In the last lecture we discussed about Coulomb's law of force, and we got expressions for force between two charges and force on a charge q due to n number of charges. So that is what we discussed in the last class. And in this lecture we will discuss about electric field intensity. And before going into the definitions and all, let's clarify a few things. Let us say we are having some positive charge at this point. So now we always say that whenever there is a charge located at some place in space, there exists a field around it. Okay, so when we draw a positive charge, we always draw field lines like this, the field lines moving away from the positive charge. So this is what we draw in general. So we say that this is the field due to this positive charge. Okay, so what is the reason behind drawing these lines like this? Actually these are imaginary lines. And why we draw these lines like this? Okay, now consider a positive charge. Now as we know Coulomb's law, let us say we take a test charge, okay, some test charge, call it as qt. So if I place the test charge qt at this point, and always remember the test charge is positive, it is positively charged. So when I keep a test charge at this point, so at this point q2 is there. So when I place this test charge qt at this point, according to Coulomb's law of force, this test charge experiences a force like this. So this is the already existing charge in this place. Now at this point we brought the test charge. Now because this test charge is positive and this is also positive, so the test charge experiences a force of repulsion from this existing charge. Okay, and this is the direction because I placed it here. Similarly, if I place this test charge here, then the direction of force will be this one. So similarly, if I place it here, this is the direction of force. As you can see, the distance is same for all these points. So what does this indicate? So these lines or imaginary lines which show in which direction a test charge will be experiencing the field due to the charge already existing at this point. Okay, so if you bring a test charge to a place or nearer to the charge which is already located in some place, then this test positive charge will experience some force. So it will experience force in this direction. If I place it here, it will experience in this direction. If I place it here, it will experience the force in this direction. So these field lines represent the force experienced by the test charge. Okay, so or else what we can say is the field lines show the direction of the force on a test positive charge if it were placed in the field. Okay, so we placed this test charge, positive charge, in this field. So these lines show the direction of force on this positive test charge. Now say Now let us consider a negative charge. Now, as we said that the test charge will be always positive. So when you place the test charge at this point, then because the test charge is positive and the existing charge is negative, there will be force of attraction. This test charge will be attracted towards this existing negative charge. So in that case, the force will drag that test charge towards the existing negative charge. So if I place the test charge here, it will be attracted in this direction. If I keep it here, it will be attracted in this direction. If I keep it here, it will be attracted in this direction. So that is the reason why we draw field lines always radially outward from the positive charge, and the field lines will be always radially inward towards the negative charge. So this is the reason. So we always consider the test charge as a positive charge, and we assume that so the charge of this QT will not disturb the charge or the field due to the existing charges. Okay, so Q2 has to be very small such that it should not disturb the existing fields. Okay, right? So this is the reason why we always draw field lines radially outward from a positive charge and radially inward towards a negative charge. So this is a very important thing to remember. So the test charge will be always positive and it will have the charge very much less, so that it should not disturb the field of the existing charges. Okay, so this is the very important point to remember. So before we discuss in electric field intensity. So now already we discussed about the Coulomb's law of force. Now let us consider the same thing. Now this is some charge Q and located at some point. So this is our QT. So this charge Q will be having some field around it. That means provided when I bring this QT, depending upon the position where I place this QT will experience either force of attraction or force of repulsion depending upon the charge Q. Okay, right? So as per our Coulomb's law, let us say this charge is positive and this is also QT is always positive. Okay, so this is R12 bar. Okay, right? So the force acts on in this direction. Let us say Q is positive, Qt is positive. So and the expression for force is F bar is given by Q Qt by 4 pi epsilon, and the position vector will be, let us say, RT bar minus R bar magnitude whole cube. Similarly here RT bar minus R bar. So this is what the expression for force is. Okay, right? Or in simple we can write down QT 4 pi epsilon R12 square AR12 bar. So this is in short what we can write down. Okay, so this is force acting on QT due to Q. So now let us bring this QT to the left side. So F bar by QT is equal to Q by 4 pi epsilon AR12 bar by R12 square. Now look at this expression clearly. So this expression is having units of newtons per coulomb, and it depends upon the existing charge Q at this point and the distance between the existing charge and the test charge. Okay, right? So it is not depending upon the amount of charge what Qt is having. Okay, right? So this parameter is called as electric field intensity or electric field strength. So electric field intensity is nothing but force per unit charge. Okay, so as a definition, if you would like to give some definition to electric field, it is simply the force per unit charge anywhere in space, because R12 changes as the position of the Qt changes. Okay, right? So F bar by Qt will give us the electric field intensity or strength. So electric field intensity is nothing but the force per unit charge at any point in space, because Qt can be placed anywhere. So as Qt position varies, only thing that varies is R12. Okay, right? So force per unit charge anywhere in space. So anywhere in space means the place where you keep Qt. Okay, right? So that is the formal definition of electric field intensity. So mathematically we should have a relation. So electric field intensity is given by, because force is a vector, electric field will also be a vector. So it is given by limit Qt tends to 0 F bar by Qt. So why limit Qt tends to 0? So I already said, so when Qt is brought into the field of Q, because this is where Q is located, so around Q some field will be existing. So when we bring Qt in the vicinity of Q, so the charge of Qt should not disturb the electric field of Q. That means the charge should be very small enough such that it will not disturb the electric field around the charge Q. So that is the reason. So we'll keep limit Qt tends to 0 F bar by Qt. But in general, most often, so electric field is written as simply F bar by Q or Qt. So force per unit charge at any point in the space is given by electric field intensity. Okay, right? So if you take two charges, Q1 and Q2, so or Q and Qt, the relation will be, let us say, so this is Qt, this is the vector R12 bar. Okay, so then the force acting per unit charge at this point is given by Q times 4 pi epsilon, and this is R12 bar, so magnitude square R12 square AR12 bar. Okay, or we can expand Q by 4 pi epsilon. So if I write R12 as in terms of position vectors, let us say the position vector of Q is R bar and position vector of Qt is RT bar. So in that case it will be RT bar minus R bar magnitude whole cube, and similarly here it will be RT bar minus R bar. So this is the expression for electric field intensity. So that is what we can write, and this is in newtons per coulomb. Okay, right? So what it gives exactly? So it is giving us at a point in space what is the force experienced per unit charge at any point in space. So provided there exists a field in that space. Okay, suppose if you are having a charge at some place, at some position, definitely there exists some field around it. So into this field if you bring some test charge, so what is the force experienced per unit charge at a particular point? So if you want to know that, that is nothing but electric field intensity. Okay, so it has units of newtons per coulomb, or more general, it has units of volts per meter also. Okay, so either electric field is having units of newton per coulomb or volts per meter. Okay, so now like we have written the force expression for force acting on a single charge due to n number of charges, we can find out the electric field intensity due to n number of charges at a point. Okay, so let us consider the same thing. So we are having some charge q1 here and some q2 here and some and some q3 here. Okay, let us say now due to these three charges there exists some field around these three charges. So let us say this is origin. Let us draw position vectors from origin to the 3 points. Okay, so let us call them as R1 bar, and this is R2 bar, and this is R3 bar. Don't call this as Q3, let us call this as Qn, because, and so on, this is Rn bar then. Okay, right? So we have considered n number of charges, Q1, Q2 and so on, Qn, so which are located at different points in space, and R1 bar, R2 bar and so on, Rn bar are corresponding position vectors. Okay, now there will be certain amount of field around this. That means the field where when the test charge is brought in, it experiences some force. Okay, right? So field is, I mean electric field is nothing but it is the area where under test charge experiences some amount of force of attraction or repulsion. Okay, right? So let us say we kept our test charge here, Qt. Now let us say this is the position vector of Qt, that is RT bar. Now in order to find out the electric field intensity due to this n number of point charges at this point in space, that is, I would like to find out what is the force per unit charge at this point. Okay, right? So what is the expression we are having earlier for force? Okay, so if I draw the position vectors, this is the distance vectors. This is the distance vector from Q1 to Qt, which is RT bar minus R1 bar. Similarly, if I draw the position vector from Q2 to Qt, so this is RT bar minus R2 bar. Similarly, if I draw the position vector, distance vector from Qn, it will be RT bar minus Rn bar. So in that case, what is the force acting on Qt? So according to Coulomb's law, so force acting on Qt is given by, because in all the expressions Qt is common, so Qt by 4 pi epsilon sigma I equal to 1 to n Qi by magnitude RT bar minus Ri bar whole cube into RT bar minus Ri bar. So this is the expression what we are having for force acting on Qt due to this n number of charges. Okay, now as per our definition, electric field intensity is force per unit charge at a point, so I will bring this Qt onto the left hand side. So F bar by Qt, So this gives me electric field intensity due to n number of charges, so which is equal to 1 by 4 pi epsilon sigma I equal to 1 to n qi RT bar minus Ri bar divided by magnitude RT bar minus Ri bar whole cube. So this is the expression for electric field intensity or electric field strength at a point due to n number of charges. Okay, right? So if you would like to find out what is the force experienced by an unit charge at a particular point in space, then that is nothing but electric field intensity. Okay, right? So every charge placed at some point will have a field around it. Okay, so as per the discussion earlier, so when you draw a positive charge, you will draw some field lines diverging away from the positive charge. Similarly, when you draw a negative charge, you will draw field lines radially inward towards the negative charge, because we always consider the test charge as positive charge. Okay, right? So this is electric field intensity. So what you can say from this, the electric field intensity depends on the charges which are creating the field and on the distance between those charges and the point where you are finding the electric field. Okay, right? So as per the discussion, so when it is positive charge, the electric field lines are radially outward. So when it is negative charge, the electric field lines are radially inward. So electric field lines represent the lines or the direction of force experienced by a test positive charge if it is placed in that field. Okay, so if I place a test charge here, it will experience the force in this direction. If I place it here, the test positive charge, it will experience the force in this direction. Similarly, because this is negative, if I place test positive charge at this point, it will experience force of attraction in this direction. Okay, so for that reason, field lines are just imaginary lines, and these lines show the direction of force on a positive point charge if it is placed in that field. Okay, so that is field lines. So with these things in mind, we can also say that field lines always begin with a positive charge and end with a negative charge. Okay, so if only one charge exists, fields will be either radially outward or radially inward. Okay, right? So these are the important points to remember in electric field intensity. Okay, right? So in the next class, we will discuss about using Coulomb's law to find electric field intensity at a point due to different charge distributions. Okay, so what do you mean by different charge distributions, right? So this we will discuss in the next class, and then we will find electric field intensity at a point due to these different charge distributions. Thank you.